Question 6 says, from a uniform solid sphere of mass m and radius r, a small sphere of radius r by 2 is removed as shown in figure. The moment of inertia of the remaining sphere about an axis A dash passing through center of sphere is. Okay, so we have to find moment of inertia when a sphere of r by 2 is removed from the entire sphere. The entire sphere had mass m, so the mass of the removed part will be, we can see that it's also a sphere and it's a uniform sphere, so mass is directly proportional to volume, and that means mass here will be directly proportional to cube of radius. So that means if I call this mass as m1, the mass which is being removed, m1 will be equal to m by 8. Further, we shall apply the theorem of parallel axis, and the result for moment of inertia of a uniform sphere about an axis passing through its center, that means about a diameter, and that result is I equals, that's a general result, 2 by 5, let's say mr square. This is the result we are going to use. So what is the moment of inertia of this sphere about axis A dash A? If I call that I1, then I1 about A dash is going to be equal to, we apply this result, so it's 2 by 5. The value of m is m by 8, and the radius is r by 2, so it's r by 2 whole square. But this is only about its own diameter, which is parallel to the axis A dash. To find moment of inertia of this part when it was there about A dash, we need to further add the term md square, applying the parallel axis theorem, where m again is m by 8 and the value of d is r by 2. That means we need to further add m by 8 into r by 2, the whole square, and we can see that further that IA dash that we are interested in finding plus I1 gives us 2 by 5 mr square. So substituting this value of I1 and simplifying, you will find IA dash comes out to 57 mr square by 160. You can check it yourself. The expressions are all there. It's a simple matter of adding and subtracting. Now this is matching with option 2. So for question 6, option 2 is correct. Let's move on to the next question now. Question 7 says, in the system shown in figure, block A of mass m is released from rest. Find the acceleration of topmost point of the solid sphere of mass m and radius r just after the system is released from rest. It is given that surface is rough enough so that there is no sliding at any point of contact. Strings and pulleys are ideal. Well, obviously the question is based on the concept of rotation. There is rolling involved here. In fact, rolling without slipping is involved here, and we have to be very careful. We have to find acceleration of topmost point of solid sphere. That means this point of the sphere just after the system is released from rest. Okay, so what we do is we first find acceleration of the center of the sphere, and acceleration of this point just after the system is released will be 2 times the acceleration of the center of the sphere, because it's a case of rolling without slipping. So let's assume that the center has acceleration A towards right. That means this block A has acceleration small a again vertically downward. So if I write the equation for the block first, we see that for the block the equation can be written as mg minus t let's assume that it has acceleration A downward, is equal to where T is tension on the block in the upward direction and the weight of course is mg. So mg minus T is ma, and for the sphere, let's say there is friction acting in the backward direction. So for the sphere, the equation is T minus friction is ma, because the center will have acceleration A only and it also has mass m. Further, let's look at the rotation of the sphere about its axis. The torque of friction is Fr, and that will be equal to 2 by 5 mr square alpha. Alpha in turn will be A by R because it's rolling without slipping. So which gives us F is equal to 2 by 5 ma. So we have equation 1, equation 2 and equation 3. If we add them all up, we get mg equals, on the left hand side, minus T minus F plus F, they all cancel, and on the right hand side we get ma into 2 plus 2 by 5, which is equal to 12 by 5 ma. So the value of A, the acceleration of the center of the sphere, is 5g by 12, which means acceleration of the topmost point of the sphere, let's call it at, will be 2a or 5g by 6. If we look at the options, well, option 4 matches with our answer, so option 4 is correct. Let's move on to the next question now. Question 8 says, a particle is moving in a circular path of radius r, centered at O, under the effect of only a central force directed towards O dash, whose coordinates are r by 2, O. So this is the point O dash. We have to find angle between velocity and acceleration of the particle when it is at point B. And these are the 4 options. Well, it's clearly given that there is only one force which is always directed towards O dash. So at point B, the force is directed towards O dash. So this is the force that is acting. So that means acceleration will also be directed towards O dash. The direction of acceleration will simply be the same as the direction of the net force on the particle. So this is the direction of acceleration of the particle. And well, at this point I just want to clarify that if in case you are thinking that the acceleration should be directed towards the center of the circle, let me just tell you that this clearly is not uniform circular motion. It's a non-uniform circular motion, right? And in that case, the direction of net acceleration won't be towards the center of the circle. Well, that being the case, we have to find angle between acceleration and velocity. Obviously, velocity will be directed along the tangent. We can see that this angle is 90 degree or pi by 2. And this angle we have to find now. So by using geometry, if we extend, this is r by 2 and this is clearly r. So we can see that if this angle, small angle, is taken as alpha, the tan alpha is equal to r by 2 by r, or simply 1 by 2. So the total angle between velocity and acceleration, let's call it theta, is pi by 2 plus alpha, which is clearly pi by 2 plus tan inverse of 1 by 2. And this matches with option 2. So option 2 is correct for question 8. Let's move on to the next question now. Question 9 says, 2 point masses m and 3m connected by string of length L are placed on smooth horizontal surface. Both the point masses are given velocity as shown. Well, the velocities are v0 in this direction on 3m and v0 in this direction for M. If the area of cross section of wire is A and Young's modulus is Y, then extension in the string is. Well, clearly the question is having multiple concepts. Of course, we will use results for the mechanical properties of solids from the topic elasticity, and to find the extension we also need to find the tension in the string, for finding which we shall apply the concepts of system of particles. Okay, so first of all, to find tension in the string we locate center of mass. But why? Because we can see that the center of mass will have a uniform velocity, constant velocity, and hence it will be an inertial frame. A frame attached to the center of mass is going to be an inertial frame. Well, the velocity of center of mass is VCM equals 3mv0 minus mv0 divided by total mass, which is 4m. On simplifying, this value comes out to be v0 by 2, and the distance of center of mass from M, let's call it R, is equal to 3ml divided by total mass, which is 4m, or simply 3l by 4. Now, in the center of mass frame, both particles are performing circular motion, and so we can apply tension T is equal to M. Its a speed with respect to center of mass will be V0 plus V0 by 2. So that means 3V0 by 2. So M 3V0 by 2 whole square divided by R, and the value of R is 3L divided by 4. Simplifying, this value comes out to be equal to, this 4 will cancel with this 4, and we have 3m v0 square. That is the tension in the string. The elongation delta L we know is tension into original length L divided by area of cross section into Young's modulus, and we substitute the value of T from here. We get it as, of course there was L also here, so if we substitute we get it as 3 mv0 square. The L gets cancelled upon AY, which is matching with option 1. So option 1 is correct. Let's go to the next question now. Question 10 says, a uniform rod of length L to be taken as a compound pendulum can be pivoted at any of point at a distance x from center of mass of rod. For what value of x, time period of pivoted rod is least? Well, the expression for time period of a physical pendulum or a compound pendulum is given as t is equal to 2 pi root I divided by mgd, where I is the moment of inertia of the body about the point of suspension, or about the axis to the point of suspension, and d is the distance of the center of mass from that axis. So in our case, the value of I will be ml square by 12, applying the parallel axis theorem, plus mx square, and the value of d is simply x. So let's get the time period t in terms of x, and the expression will be t is equal to 2 pi under root of m into L square by 12 plus x square divided by mg into x, and this will obviously depend on the value of x. So now we want the time period to be the least. Well, when the time period is least, the t square is also the least, and we can write expression for t square as, so some constants we can simply remove as a factor. So that constant will be 4 pi square by g square. Let's simply write it as a, right, where as I told you a is 4 pi square by g. So t square is a into L square by 12x plus x. And for t square to be minimum, d by dx of t square has to be 0. We can apply this, and doing this gives us L square by 12 into minus 1 by x square plus 1 is equal to 0, which gives us x is equal to L by root 12, or that means L by 2 root 3. If you look at the options, it is matching with option 4. So option 4 is correct. Let's go to the next question now.